Electric charge has captivated human curiosity for centuries, tracing back to ancient Greece. Thales of Miletus, around 600 BC, made a groundbreaking observation. Rubbing amber with wool could attract light objects like straw and bits of paper. This phenomenon led to the term electricity, derived from the Greek word electron, which means amber. This early discovery laid the foundation for understanding electric charge and its implications in the natural world. As scientific inquiry progressed, many pairs of materials were identified that exhibited similar behaviors when rubbed together. For example, if two glass rods are rubbed with wool or silk, they repel each other, while the glass rod attracts the wool or silk. This intriguing behavior extends to other materials as well. When plastic rods are rubbed with cat fur, they repel each other but attract the fur. These observations led scientists to conclude that there are two distinct types of electric charges, positive and negative. The concept of electric charge is fundamental to understanding how materials interact with one another. When a glass rod is rubbed with silk, it acquires a positive charge, while the silk gains a negative charge. This process of electrification occurs due to the transfer of electrons, the negatively charged particles within atoms. When the electrified glass rod comes into contact with the silk, they no longer attract each other. This phenomenon illustrates the principle that unlike charges attract and like charges repel. The American scientist Benjamin Franklin played a pivotal role in naming these charges. He established the convention that the charge on a glass rod or cat's fur is positive, while the charge on a plastic rod or silk is negative. This nomenclature has persisted through the centuries, allowing for a clearer understanding of electric charge interactions. To detect electric charge, one of the simplest and most effective tools is the gold leaf electroscope. This device consists of a vertical metal rod housed in a box with two thin gold leaves attached to its bottom end. When a charged object touches the metal knob at the top of the rod, charge flows onto the leaves, causing them to diverge. The degree of divergence serves as an indicator of the amount of charge present on the object. This simple yet effective apparatus has been instrumental in demonstrating the principles of electric charge. All matter is composed of atoms, which are typically electrically neutral. However, within these atoms, charges exist that can become unbalanced. The forces that hold molecules and atoms together are fundamentally electrical in nature, arising from the interactions between charged particles. This electric force is pervasive, influencing various aspects of life, from the adhesive forces of glue to the surface tension of liquids. To electrify a neutral body, it is necessary to add or remove one kind of charge. When a body is said to be charged, it refers to an excess or deficit of charge. In solids, some electrons are less tightly bound to their atoms and can be transferred from one body to another. For instance, when a glass rod is rubbed with silk, some electrons from the rod are transferred to the silk cloth. As a result, the glass rod becomes positively charged, while the silk becomes negatively charged. Importantly, no new charge is created during this process. Instead, the total charge remains constant, with only the distribution of electrons changing. Electricity behaves differently in conductors and insulators. Conductors are materials that readily allow the passage of electricity through them. They contain electric charges, primarily electrons, that are relatively free to move within the material. Metals, the human body, and the earth are prime examples of conductors. In contrast, insulators, such as glass, porcelain, plastic, nylon, and wood offer high resistance to the flow of electricity. Most substances can be classified as either conductors or insulators, based on their ability to conduct electric charge. When a charge is transferred to a conductor, it quickly distributes itself over the entire surface of the conductor. This property explains why a nylon or plastic comb becomes electrified when combing dry hair or rubbing it against another material. The charges on the comb remain localized, allowing it to attract light objects. Conversely, when a charge is applied to a metal object, such as a spoon, the charge dissipates quickly into the ground, as both the metal and the human body are conductors of electricity. Interestingly, a metal rod with a wooden or plastic handle can still show signs of charging when rubbed, provided the metal part does not touch anything conductive. This demonstrates that even conductors can exhibit electrification under certain conditions, highlighting the complexity of electric charge interactions. Understanding electric charge and its behavior is crucial, as it underpins many aspects of science and technology. From the simple static electricity experienced when walking across a carpet to the complex electrical systems that power modern society, electric charge plays a vital role. The study of electric charge not only enhances comprehension of fundamental physics, but also paves the way for innovations in electronics, energy production, and communication technologies. As research continues, the exploration of electric charge promises to unveil even more fascinating insights into the nature of matter and energy. Electric charge is a fundamental property of matter, existing in two distinct types, positive and negative. These charges interact in such a way that they can cancel each other out, leading to a neutral state. When dealing with very small charged bodies, such as electrons and protons, they are treated as point charges. This means that all the charge content of the body is assumed to be concentrated at a single point in space, simplifying calculations and understanding of their interactions. In a system containing 2 point charges, denoted as Q1 and Q2, the total charge of the system can be easily calculated by simply adding these charges together algebraically. This process illustrates that charges behave like real numbers, meaning they add up as scalars. For a system with multiple charges, say n charges, the total charge can be expressed as Q1 plus Q2 plus Q3 up to plus Qn. This property of additivity is crucial for understanding electric charge interactions. One important distinction between charge and mass is that while mass is always a positive quantity, charge can be either positive or negative. This dual nature of charge necessitates careful attention to the signs when performing calculations. For example, consider a system with 5 charges, plus 1, plus 2, 3, 4, and 5. The total charge in this case would be calculated as plus 1, plus 2, 3, plus 4, or 5, resulting in a total charge of 1. This example highlights the importance of proper sign usage in charge calculations. Another fundamental property of electric charge is its conservation. When two bodies are charged through processes like rubbing, electrons transfer from one body to another. This transfer occurs without the creation or destruction of new charges. Essentially, whatever charge one body gains, the other body loses. In an isolated system, which consists of multiple charged bodies, charges may redistribute among the bodies due to their interactions. However, the total charge of the isolated system remains constant throughout these interactions. It is crucial to understand that while charge-carrying particles can be created or destroyed in certain processes, the net charge of an isolated system is always conserved. For instance, in particle physics, a neutron can decay into a proton and an electron. In this process, the proton carries a positive charge, while the electron carries a negative charge. The total charge before and after this transformation remains zero, demonstrating the principle of charge conservation. Moving on to the quantization of charge, it is experimentally established that all free charges are integral multiples of a basic unit of charge, denoted as E. This means that the charge Q on any body can be expressed using the formula QE(n), where n is any integer, which can be positive, negative, or zero. The basic unit of charge, E, corresponds to the charge carried by a single electron or proton. By convention, the charge of an electron is considered negative, represented as E, while the charge of a proton is positive, represented as plus E. The concept of quantization of charge was first suggested by the experimental laws of electrolysis discovered by the English scientist Michael Faraday. This idea was later experimentally demonstrated by Robert Millikan in 1912 through his famous oil drop experiment. In the International System of Units, SI, the unit of charge is called a coulomb, denoted by the symbol C. 1 coulomb is defined as the amount of charge that flows through a conductor in 1 second when there is a current of 1 ampere. The value of the basic unit of charge, E, is approximately 1.1602 × 10 to the power of minus 19 coulombs. This means that a charge of 1 coulomb is equivalent to approximately 6,010 to the power of 18 electrons. In the realm of electrostatics, charges of such large magnitudes are rarely encountered in everyday situations. Therefore, smaller units such as microcoulombs, 1 mC(e^10 to the power of minus 6 coulomb, and millicoulombs, 1 millicoulomb equals to 10 to the power of minus 3 coulomb, are often used for practical purposes. Since protons and electrons are the only basic charges in the universe, all observable charges must be integral multiples of E. This means that the charge on any body can increase or decrease in discrete steps of E. However, this step size is incredibly small. At the macroscopic level, where charges are typically measured in microcoulombs or larger, the discrete nature of charge becomes less apparent. This phenomenon can be compared to a dotted line that appears continuous when viewed from a distance. Although the line consists of many closely spaced points, it gives the illusion of continuity. Similarly, at larger scales, charges appear continuous because the increments of E are negligible compared to the total charge being measured. For instance, a charge of 1 microcoulomb contains approximately 10 to the power of 13 electronic charges, making the individual steps of E practically invisible at this scale. However, at the microscopic level, where charges are measured in tens or hundreds of E, the quantization of charge becomes significant. In these scenarios, charges can be counted and appear in discrete lumps, making the quantization of charge an essential concept in understanding electric phenomena. The scale of measurement is crucial in grasping the behavior of electric charge, as it influences how charge is perceived and utilized in various applications. Electric charge possesses distinct properties. It can be positive or negative, is conserved in isolated systems, and is quantized in integral multiples of E. Understanding these properties is fundamental to grasping the principles of electricity and electrostatics, paving the way for advancements in technology and science. Coulomb's law is a fundamental principle in electrostatics that quantifies the force between two-point charges. When the linear dimensions of charged bodies are significantly smaller than the distance separating them, they can be treated as point charges. This simplification allows for a clearer understanding of the interactions between charged particles. Coulomb discovered that the force between two-point charges varies inversely with the square of the distance separating them and directly with the product of their magnitudes. This relationship can be mathematically expressed with the formula F equals K multiplied by Q1 multiplied by Q divided by R squared. In this equation, F represents the force between the charges. Q1 and Q2 are the magnitudes of the two charges, R is the distance between them, and K is a proportionality constant. The value of K is approximately 9 multiplied by 10 to the power of 9 Newton-meter squared per Coulomb squared in SI units. To measure the force between charged metallic spheres, Coulomb employed a torsion balance, a sensitive instrument that allowed for precise measurements of forces. When the separation between two charged spheres is much greater than their radii, they can be effectively treated as point charges. This assumption simplifies calculations and helps in understanding the fundamental interactions at play. Coulomb devised an innovative method to explore charge distribution. By charging one metallic sphere with a charge Q and then bringing it into contact with an identical uncharged sphere, the charge would spread evenly across both spheres. By symmetry, each sphere would then carry a charge of Q divided by 2. This process could be repeated multiple times, resulting in charges of Q divided by 2, Q divided by 4, and so forth. This iterative approach allowed Coulomb to systematically investigate how charge distribution affected the force between the spheres. By varying the distance between fixed pairs of charges and measuring the resulting forces, Coulomb established a comprehensive relationship that defines the interaction between electric charges. This experimentation revealed that the force is not only dependent on the magnitudes of the charges, but also on the distance separating them. Remarkably, Coulomb derived this law without knowing the explicit magnitude of the charge itself. This foundational principle later became instrumental in defining the unit of electric charge, known as the Coulomb. In practical terms, 1 Coulomb is defined as the amount of charge that, when placed 1 meter away from another charge of the same magnitude in a vacuum, experiences a repulsive force of 9 multiplied by 10 to the power of 9 newtons. Due to its large size, the Coulomb is often too cumbersome for practical applications in electrostatics. Therefore, smaller units like microcoulombs, 10 to the power of -6 coulombs, and millicoulombs, 10 to the power of -3 coulombs, are frequently used in everyday calculations. Coulomb's law can also be expressed in terms of the permittivity of free space, denoted as epsilon 0. The relationship can be rewritten as K equals 1 divided by 4 pi epsilon 0, where epsilon 0 is a fundamental constant in electromagnetism. The value of epsilon 0 in free space is approximately 8.854 multiplied by 10 to the power of -12 Coulomb squared per Newton meter squared. This constant plays a crucial role in determining the strength of the electric force in different media. To express Coulomb's law in vector notation, let the position vectors of charges Q1 and Q2 be represented as R1 and R2, respectively. The force exerted on charge Q1 due to charge Q2 is denoted as F12, while the force on charge Q2 due to charge Q1 is denoted as F21. The vector leading from charge 1 to charge 2 is represented as R21, calculated as R2 minus R1. Conversely, the vector from charge 2 to charge 1 is denoted as R12, which equals minus R21. The magnitudes of these vectors are denoted as R21 and R12 respectively, and it is important to note that R12 equals R21 in magnitude. The direction of a vector is indicated by a unit vector along the vector. Coulomb's force law can then be expressed in vector form as F21 equals divided by 4pi epsilon 0 multiplied by Q1 multiplied by Q2 divided by R21 squared multiplied by R cap 21. This vector notation provides a more comprehensive understanding of the forces at play between charged particles. Coulomb's law aligns with Newton's third law of motion, confirming that the forces between two charges are equal in magnitude and opposite in direction. However, when charges are placed in a medium rather than in a vacuum, the situation becomes more complex due to the presence of other charged constituents in the matter. The interactions between charges in different environments can lead to various phenomena, such as polarization and dielectric effects. This law not only lays the groundwork for electrostatic calculations, but also serves as a foundation for further studies in electromagnetism and physics as a whole. The implications of Coulomb's law extend beyond theoretical physics, influencing technologies such as capacitors, insulators, and various electronic devices. In the study of physics, the concept of electric fields is essential for understanding how charged particles interact with one another. Consider a point charge, labeled Q, positioned at the origin of a coordinate system. When another charge, referred to as Q, is placed at a distance r from Q, Coulomb's law indicates that charge Q exerts a force on charge Q. This leads to an intriguing inquiry. What occurs when charge Q is removed from the vicinity of charge Q? Is there nothing remaining at point P, where Q once existed? To explore this question, early scientists introduced the concept of the electric field. An electric field is a representation of the influence that a charge exerts on the space surrounding it, even in the absence of other charges. Charge Q generates an electric field that extends throughout the surrounding area. Consequently, when charge Q is introduced at point P, it interacts with the electric field created by charge Q, resulting in a force acting on Q. The electric field E produced by charge Q at a distance C can be mathematically expressed using the formula E x1 for per QR2 while R. In this equation, EZO represents the vacuum permittivity, and R is the unit vector pointing from the origin to the point R. This formula illustrates the inverse square relationship of electric forces, indicating that the strength of the electric field diminishes with the square of the distance from the charge. The term field signifies how a distributed quantity, which can be either a scalar or a vector, varies with position. The influence of charge Q is encapsulated in the electric field it generates, which exists at every point in three-dimensional space. This concept allows physicists to visualize and calculate the forces that would act on charges placed within the field. It is important to note that charge Q also exerts an equal and opposite force on charge Q. This interaction can be viewed as a mutual relationship between charge Q and the electric field produced by charge Q. When charge Q is positioned at vector R, it experiences a force F, defined by the equation F R equals Q E R. The SI unit for electric field strength is newtons per coulomb, providing a standardized measure of the force experienced by a unit charge in an electric field. The electric field at any point in space can be defined as the force that a unit positive charge would experience if placed at that point. Charge Q, responsible for generating the electric field, is referred to as the source charge, while charge Q, which experiences this field, is known as the test charge. It is crucial to recognize that the source charge Q must remain stationary for the electric field to be accurately defined. However, when charge Q is introduced nearby, charge Q experiences a force due to the presence of Q, which can lead to movement. Several key points about electric fields are vital for a comprehensive understanding. 1. To maintain charge Q in place while considering the influence of charge Q, unspecified forces are often employed. This may seem unusual, but it is a practical solution in experimental setups. For instance, when examining the electric force on a test charge Q near a charged planar sheet, the charges on the sheet are held in position by forces from the internal constituents of the sheet. This ensures that the source charge remains undisturbed while allowing for the study of electric fields. 2. The electric field, E, created by charge Q, is defined operationally through the test charge Q, yet it remains independent of Q itself. This independence arises because the force F is proportional to Q, making the ratio FQ constant. Therefore, the electric field E depends on the spatial coordinates, varying with the position of charge Q around charge Q. This means that different positions of charge Q will yield different values of the electric field E, illustrating the field's dependence on the spatial arrangement of charges. 3. The direction of the electric field is determined by the nature of the source charge. For a positive charge, the electric field radiates outward, indicating that the force on a positive test charge would also be directed away from the source charge. Conversely, if the source charge is negative, the electric field points inward, signifying that a positive test charge would be attracted toward the source charge. 4. The magnitude of the force F acting on charge Q due to charge Q is contingent on the distance U between them. Consequently, the magnitude of the electric field strength also relies solely on this distance. At equal distances from charge Q, the electric field's strength remains consistent, demonstrating spherical symmetry. This means that the electric field's magnitude is uniform across a sphere centered on the point charge, reinforcing the idea that electric fields extend throughout space. Understanding electric fields is fundamental to grasping the interactions between charged particles. The electric field concept clarifies how forces act at a distance and lays the groundwork for exploring more complex electromagnetic phenomena. As scientists continue to study these fields, the implications for technology and our understanding of the universe grow ever more profound.